Okay, welcome to our first video lecture. We're going to have one of these for every class essentially this semester. So you're going to get into the routine of just watching a short video. I'll try and keep them to 10 to 15 minutes. So watch a short video before each class and then complete the homework that follows directly from the video. I'll collect that homework in class. And then there's also a short quiz each day. The quiz will be essentially identical every day, but I want you to complete it each day. And it's due an hour before class starts so that I have time to look at your responses to the quiz, and that will guide how we start each class period. So okay, our topic today is inequalities. Each day we'll talk about a section or a part of a section. Today it's section 1.1 in the text. As you listen to this video, you should take notes, treat it like a class. So take notes. The advantage of the video is you can pause it, you can speed it up if I'm talking too slowly, you can slow it down if I talk too fast. You should take notes, and they'll be the basis of what we use to work on in class. And think about what's going on in the videos compared to what you already know. You've probably seen a lot of the topics that we're going to talk about in this class, so you've obviously already met inequalities. So as I talk, think about what I'm saying in light of what you understand about inequalities, and if there's a difference there, that gives you some questions to ask, to think about. Bring them to class. That's the kind of thing we'll be talking about, and we'll be doing lots of problems that kind of explore inequalities in more depth. So, having said that, let's start talking about inequalities. Our first section here is inequalities, obviously, and I'm just going to do a few examples. Let's start with the inequality x is greater than 2. We're going to define a few terms. So the first term here that we need is the idea of a solution set. So what values for x solve that inequality, satisfy that inequality? And so the solution set, that's the thing we're interested in here, that solution set for our inequality is, well, this is a pretty straightforward inequality, so the solution set is all the values of x which are greater than 2. So we could write that as, using set builder notation, all the real numbers x such that x is greater than 2. That really doesn't get us very far, right? Because it's essentially the inequality we already had. Another way of doing it is talking about the interval notation way of writing that, which would say all the numbers from 2 to infinity. And so those two statements are equivalent. This is the solution set for our inequality. It's all the numbers that are greater than 2. We can also have a graph of the solution set for this inequality. So the graph of our inequality is essentially going to be a straight line. It's great how this turns into a straight line. And starting from the number 2 along the number line, we're going to take all the values from 2 onwards, but not including 2. And so this solution set, this graph of the solution set, in fact, is all the numbers from 2 onwards, off to infinity. So larger and larger numbers. This round bracket that I use here shows that 2 is not included in the set. An alternative way of doing this that you might have seen before is to just draw a dot there that's not coloured in. The fact that it's not coloured in means that we're not including it. And so 2 off to infinity, there's an equivalent graph of our solution set. So we've got a solution set, and we can draw graphs of the solution set. We can give that solution set in interval notation over here. We can do it here using the set builder notation. There's different ways that we can talk about the solutions of this inequality. So this is our basic language. And inequalities have a bunch of properties. And this theorem up here, which is straight from the textbook, theorem 1.1.1, gives us, surprisingly, the properties of inequalities. And let's take an example that lets us kind of explore that. Let's suppose we want to solve the inequality 12 minus 3x is, let's say, less than or equal to 5. There's an inequality. Notice up here we had a greater than, now we have a less than or equal to. This theorem is written in terms of a less than here, but I could go and change this to a greater than and that to a greater than, and each one of these change the inequality, and the properties sort of similarly hold. So if I want to solve this inequality, what I mean is I want to find the solution set. So we can use these rules from the theorem to do so. So this says that I can take an inequality, A is less than B, in our case it's A, here's our A is less than or equal to B, which is 5. I can take that inequality and add the same number to both sides, this number C. C is a non-zero real number. So I can add C to both sides. The c that I might add to both sides here is minus 12. So I might take 12 minus 3x and add minus 12. You know, I can think about that as adding minus 12. I'm doing this in a really kind of awkward way, but I'm just showing you how the theorem is telling us what's going on. The reason I added minus 12 is because those two numbers cancel. That leaves us minus 3x is less than or equal to, while combining this, minus 12 plus 5, that sounds like minus 7 to me, maybe. So there is a slightly simplified inequality. This inequality is equivalent to the one up here. It's not yet giving us the full solution because we don't know what the x's are. So let's go on and use these second two rules. These second two rules say that if you've got the product, you've got a constant factor on each side of an inequality, then you can divide it out in appropriate ways and get something that's equivalent to a is less than b. So if c is a positive number, you just divide it by both sides and you're left with a is less than b. But if c is a negative number, you have to change the inequality. So this says AC is greater than BC. I'm going to divide the whole thing by this negative c, and it'll turn this greater than into a less than. And you've probably seen this before. So I'm going to say divide, in our case, by this number here, negative 3. And, you know, the negative 3 is not over there, but I'm going to move it over there. I'm going to say negative 3x over here. Let me just rewrite it again. Sorry for the bad writing. I'm going to divide that, and if I divide the negative 3 on the other side, so I'm going to put the negative 3 there, this changes the less than into a greater than, and we had less than or equal to begin with. So now we've got greater than or equal to. And notice what I didn't write. This would not be correct. If I'd done this, x is, well, let's take this minus 3 and divide it over, right? Divide it over minus 3 divided by the minus 3 there. You know, I can put the minus 3 here and divide both sides. That's not right. That can't possibly be right, because this side simplifies to x, this side simplifies to 7/3, so that's exactly the same statement here, except this says less than or equal to, and this says greater than or equal to. So if you do the division, you must change the sign, or change the inequality. So I've done the division, I divided by minus 3 on both sides here, I've done the division, which means I have to have changed the inequality as well. So be careful about what you write. In fact, I would not write any of this. Go straight to changing the inequality and putting it here. I'm sure this will come up and we'll talk about this some more in class. So if I draw the graph of this solution set, the graph is going to be a straight line. You know, it's all the numbers greater than or equal to greater than or equal to 7/3, because I didn't quite say that, but another way of writing what we have here, just simplifying, is x is greater than or equal to 7/3. So I'm going to take the point, if you like, 7/3 here, and then all the values that are greater than or equal to that. So there's the graph of our solution set in the interval notation. I can't spell. The interval notation here, we have 7/3 off to infinity. So there we go. Okay, so let's talk a little about simultaneous inequalities. You've probably seen these before. What we have here is an inequality that is essentially two inequalities written together. It means the two inequalities that minus 5 is less than or equal to 2x plus 3, and at the same time, that 2x plus 3 is also less than or equal to 2. And so we could use the ideas we've just talked about to solve both of these inequalities separately. But in fact, it's more efficient to solve the two of them together by using that theorem, but doing it in a way that we do it simultaneously. So the first thing you would do here, using our theorem, is move the 3 away and then divide the 2 out. So I'm going to do that to both sides at once. So I'm going to subtract the 3 onto the other side in both cases. So I'm subtracting the 3 away, so it's gone here, and on the other side, we end up with that. So just simplifying that, we've got 2x is now greater than or equal to, that feels like minus 8, and on the other side, we've got minus 1. And so we can now use the second part of our theorem to divide the 2. Because the 2 is positive, we can just divide it on both sides. We don't need to change anything. We get minus 8 over 2 is less than or equal to x, which is less than or equal to 1 over 2. And so x is in the region between minus 4 and minus 1/2 inclusive. So if I draw a graph of that solution, the graph looks like the graph is the region between minus 4 and minus 1/2. And there's no reason to do anything other than just draw the region we're interested in. We're only interested in this piece of the solution set. So I can use solid dots here to mark the -4 on the -1/2, or I can just use the square brackets. That's our graph of the solution. And we can also write it in interval notation. We could use this to build a set builder notation form of it. In interval notation, the solution set is between -4 and -1/2 with the square brackets because we're including the endpoint. So that's a simultaneous inequality. It allows us to do both of these inequalities at once. You should never get a simultaneous inequality where these things point the other direction because it's not possible. Let's look at a quick example of that. If I actually point these inequalities the other way, so if I have this, I'm just going to say, not possible. Don't write this down as if it's true. This is not possible. You cannot have a number which is bigger. Well, I don't want bigger. I said we needed them the other way around. So you cannot have a number which is, let's say, both less than 0 and, because remember what this means to write them together, you can't have a number that satisfies that. There is no number x which is both less than 0, reading it that way, and bigger than 1. Anything that's less than 0 is automatically not bigger than 1. So this has no solutions. This is not possible. Never write inequalities that way around. There should always be, if you're going to have a simultaneous inequality, the equality sign should go this way. They should both be less than. So that's just a nice little note. Okay, so our last thing to talk about with inequalities is the idea of nonlinear inequalities. So our job here is to solve this inequality, but it is not linear. It's not linear because, as you can see, it's not just something that involves x's and coefficients and things added to it. Think about each of these equations. Each of these equations where x is involved, x is never squared or cubed, there's no square roots. It's just some linear function of x, and we're going to talk about linear functions more later on. But this is just a linear function, some multiple of x plus perhaps some constant. And each of the inequalities we've looked at have had that form. Each of these is linear. Now we're into a new class, which is nonlinear inequalities. We know it's nonlinear because x is squared. Or maybe it could be cubed. Or maybe you've got 1 over x. None of those things are linear. So when you're looking for nonlinear functions, you're looking for things like x squared, or x cubed, or the square root of x, or 1 over x, or things like that. So they're examples of quantities that are nonlinear. We want to solve this inequality, and we're going to do it using the ideas we have from linear inequalities. So the first thing to do is always to rearrange these things so that everything's on the one side and you're comparing to 0. And that's obviously not correct because I need to subtract the 6 over and subtract the x over, and so I get x squared minus x minus 6. All right, so we have this inequality. We're now comparing it to 0. For nonlinear inequalities, that's always what we do. We always compare to 0. In other words, we move everything on one side of the expression, we have an inequality, and then we have a 0. And then we factor. And we factor this quantity. And I'm sure you can see how to factorize this relatively simple quadratic. We're going to be doing more factoring as we go. But I've just factorized the quadratic. And the idea here is I've got two quantities that are multiplied together and they give a number bigger than 0. Well, the only way that can happen is if both of them are positive or both of them are negative. If both terms are negative, then when you multiply them together, you get a positive. And so I want this whole quantity to be positive. So there's essentially two possibilities. They're both positive or they're both negative, these factors, the x plus 2, the x minus 3. The way we're going to actually do that is using what's called a sign chart. And I've begun to draw a basic sign chart here for us to see. So I've taken the factorization of this nonlinear polynomial. Anytime you see a nonlinear inequality, you're going to factorize, compare it to 0, and build a sign chart. So I'm taking the factor x plus 2, I'm taking the factor x minus 3, I'm throwing them both in this chart. Essentially, these are rows on a column, on a little grid. And then I'm taking the whole product. If I multiply those two things, I get this, and that's the quantity we're interested in, right? That's the quantity we're comparing to 0. So what I'm going to do is find the key places. I'm going to find the places where those things change sign. So I'm going to ask, when is x plus 2 equal to 0? And when is x minus 3 equal to 0? Well, we know that x plus 2 is equal to 0 when x is minus 2, and x plus x minus 3 is equal to 0 when x equals 3. And I'm going to take those two key points and I'm going to put them on my number line down here. This is just a number line. Minus 2 and 3. They're the only important points on the number line because they're the only points where this thing is 0, and therefore that's the only places where this quantity can change sign, from go from positive to negative. The only way x plus 2 can go from being positive to being negative is if it goes through 0. And when is it 0? Right here at minus 2. So now I'm just going to calculate these quantities. I'm going to pick a value and I'm going to calculate the quantities at those values. So I'm going to pick the value minus 2, let's say. I'm going to calculate the value of x plus 2 at the point minus 2. Well, minus 2 plus 2 is 0. Similarly here, I'm going to take the point minus 2, I'm going to plug it into x minus 3, and I get minus 5. Well, that's negative. I don't care whether it's minus 5 or minus 5,000. I just care that it's negative. Let's do the same with this point over here at the point 3. The point 3, if I plug it into the bottom one, I get 0 out. If I plug it into the top one, I get 3 plus 2. Well, that's positive 5. Don't care about the number. I just care that it's positive. And then we're going to do the same thing in between those regions. So let's make this a different color so we can see. We're going to pick some point in between these regions somewhere. 0 is in between, so we could use 0. So plugging 0 in here, 0 plus 2, that's equal to 2. That's positive. When I go over here and I plug 0 in and I subtract 3, I get a negative number. Pick a number here, bigger than 4. Bigger than 3, I could use the number 4. Plugging 4 in, we get 6, that's positive. Plugging 4 in, we get 4 minus 3 is 1, that's positive. On this side, I pick a number less than minus 2, so I'm going to go over to here, let's say minus 3. Plugging that in, I'm sorry, that's very, very difficult to read, but that says minus 3. So plugging minus 3 in, we get minus 3 plus 2. Well, that's negative, right? This is minus 3. Minus 3 plus 2, that's negative. Minus 3, that's negative 6, that's negative. There we go. We've got all of those things. What we actually really care about is this quantity, whether it's positive or negative. And it's the product. So negative and negative makes positive. Oops, positive. 0 and minus makes 0. Positive and negative makes negative. Positive and 0 multiplied together gives 0. Positive and positive multiplied together gives positive. And now the question that we want to answer is x squared minus x minus 6 greater than 0. Well, x squared minus x minus 6 is this. So it's greater than 0 when? Well, looking at this, it's greater than 0 in two regions. It's greater than 0 over here. It's greater than 0 over here. So it's greater than 0 when x is below minus 2, and it's greater than 0 when x is above 3. So in other words, it's greater than 0 in this region. No, I'm drawing the graph. And it's greater than 0 in this region. So the interval where that inequality is true is the interval from minus infinity up to minus 3, and then union continuing from 3 to infinity. I'm sorry, that's a minus 2. From minus infinity to minus 2, this region. Yeah, I didn't color it right, did I? From minus infinity to minus 2, so it's there. There we go. Now I've colored it right. From minus infinity to minus 2, and then from 3 to infinity. That's the solution set of this nonlinear inequality. Every time we see a nonlinear inequality, we're going to make a sign chart. So I hope you thought that was fun. We're going to do a bunch more of this in class. I want you now to have a go at the daily homework. There's a couple of problems related to this stuff, and then fill out the quiz, and I'll see you in class.